Look what I got you. My little bubby's gonna look like a little man. You know, we probably already know what a function is, or at least I'd be willing to bet we have a general idea. Your high school class might have talked about like the vertical line test, or a black box that turns inputs into outputs, or being given an equation, or charts, or a table, or a graph. These are all okay-ish, but let's be a little bit more precise. We'd like to be able to have an idea of a function without having to see its graph, or being handed an algebraic expression for computing it. Also, we really want to define a function based on, at the very least, its domain. In that sense, high school might not have actually been explicit enough, since in high school we usually work with functions with implicit domains. But really we want to consider something like this distinct from something else like this. Because even though those two algebraic expressions might seem the same, one I can plug 2 into, and the other I can't. So they have different domains. They ought to be different functions. So a function from x to y, for us, will be a collection of ordered pairs, inputs, comma, outputs, such that there's no repetition in the first coordinate, and every point in x is accounted for. That's just a slick way of saying that every input has exactly one output, which is just the vertical line test we all know and love. Notice that when we have a function f from x to y, which is to say you plug in elements of x and you get elements of y, then we immediately get a function from the power set of x to the power set of y, which is to say you can plug in whole subsets of x and get out whole subsets of y. And you do this in the totally natural way. Evaluate your function on every point in that subset. So we can ask for something like f of capital A, where capital A is a subset of x, and all it is the set of f of little a's in y, where little a lived in A. But this is super good, because topologies are built out of subsets. All a topology is a collection of distinguished subsets that we decided to call the open ones, remember? So there ought to be a way to require a function between two topological spaces to not only carry the information between sets x and y, but also between the topologies tau of x and tau of y. Of course, not every function will do this. I mean, most likely a function that sends points haphazardly without any care to where they go isn't going to respect the topology structure. But some functions will play nice with the topology, and those are the functions we care about today. There's a bit of a problem though. Remember that if we've got some topology, then the open sets are closed under arbitrary union and closed under finite intersection. So any function that carries this topological structure has to carry this fact as well. Except, notice that if I hand you any two subsets of x, call them A1 and A2, then even though f of A1 union A2 is f of A1 union f of A2, it turns out that f of A1 intersect A2 is not f of A1 intersect f of A2. Perhaps worse still, f of x minus A is not y minus f of A. So thus complements don't seem to behave nicely either, and therefore we can't go back and forth between open and closed sets. So our approach to define a function that respects topologies seems misguided. We can't just do something naive like send open sets to open sets. Fortunately, we have a different tool we can use though, preimages. The preimage of a subset B of y is the set of elements in x that map to B. Don't get tripped up by the notation, this isn't an inverse function. But preimages do play nice with our set operations. You can check from the definition that if B1 and B2 are subsets of y, then the preimage of B1 union B2 is the preimage of B1 union the preimage of B2. The preimage of B1 intersect B2 is the preimage of B1 intersect the preimage of B2. And x minus the preimage of B is the preimage of y minus B. So this motivates the definition for the special class of functions that we were thinking about earlier. We call a function continuous if preimages of open sets are open. And continuous functions are exactly those that carry the topological information along with them. But hold on, Eric, I hear you say. that's what a continuous function is? There's tons of different ways of defining continuous functions. Depending on your level of sophistication, you know some or all of these. You can draw its graph without lifting your pen. The function value equals the limit value. Epsilon delta argument. It commutes with limits. It commutes with sequences. The oscillation is 0. Preimages of open sets are open. Preimages of closed sets are closed. If you start with the neighborhood of a point f of x, then you can find a neighborhood of x that maps inside the neighborhood of f of x. The image of the closure sits inside of the closure of the image. Preimage of the interior sits inside of the interior of the preimage. Go on, prove some of those equivalences. Go on, do it. I'll wait here. Find some more while you're at it. It's okay. No, really. Go on. Go do it. Go prove those equivalences. Get. So, continuous functions give us a way to map topological information between topological spaces. So, a continuous function, f from x to y, starts with information in x and spits out information in y. But here's the kicker. What if you could go backwards? What if you could take topological information on y and then get topological information on x? And what if you could do it compatibly with f? Before we go any further, maybe you don't have the intuition for it just yet, but let's say right here, a priori, there's no reason that this has to happen. In fact, let's unpack a little bit about how this might come about. In order for this to happen, f at least needs to be a bijection. That means that on the set level, forget about topology even, we need to be able to go back and forth. So f needs to have an inverse function, which we'll write as f superscript minus 1, but now remember that this is an honest-to-God function. But f inverse can't just be a function. Remember, it needs to carry the topological information too. So f inverse had better be continuous. So now we require that not only f, but f inverse as well is continuous. And this would give us a way to go back and forth carrying topological information between x and y. This construction is so important, we give it a name. A continuous function between topological spaces with a continuous inverse is called a homeomorphism. Or it's just an isomorphism in the category of topological spaces, but don't worry, we'll get there. Whenever we get a new definition, like a continuous function or a homeomorphism, it's always important to see a couple of examples. As far as continuous functions go, we actually have a lot in our back pocket already. Think back to high school where the definition was you can draw it without lifting your pen. And if you proved the equivalences back there, then you know that any function where you draw it without lifting your pen is continuous the way we think about continuity. So, at least for functions to and from the real numbers, we have plenty of examples of continuous functions. Polynomials, exponentials, etc. Okay, what about homeomorphisms? Well, for a silly example, any identity function works. Let's check for ourselves. It's not too hard to see that it's continuous. Use our definition, preimages of open sets are open, that it has an inverse, and that inverse is continuous. And just hell, if our intuition is that homeomorphisms carry the topological information back and forth, then an identity function had better do that. Okay, so what about a less silly example? We can show that R is homeomorphic to -1, 1, or for that matter, any open interval. To do that, we just need to build a homeomorphism. So here's one example. Let f from R to -1, 1 be f of x is x over the absolute value of x plus 1. Feel free to check however you want to that f is continuous. And it's also bijective, and its inverse is f inverse of y is y over 1 minus the absolute value of y, which is also continuous. Okay, but I claimed R is homeomorphic to any open interval, so how do we show that R is homeomorphic to a different one? Either cook up a specific map from R to that interval that has a continuous inverse, or cook up a homeomorphism between -1, 1 and your interval, and then compose. And stay tuned until the end of the talk where I say the magic words that compositions of continuous functions are continuous. We should also point out a non-example. In particular, not every continuous bijection needs to be a homeomorphism. The classic example is, let's start with an interval and a circle. Remember that we can express any point on the unit circle in terms of its angle off the horizontal. And so any point on the circle can be expressed as a degree from 0 to 360. But let's deal with radians because we're big guys and gals and NB pals. So that means that we have a function, f, from 0 to 2 pi to s1, where you give me any radian between 0 and 2 pi, and that determines a point on the circle s1. And yeah, there's other s's. And we throw away 2 pi itself because that's just the same as 0 radians. Now, this is a continuous function, and here's the animation convincing you so. And it is bijective as well. because every angle measure gives me a unique point on the circle, and every point gives me a unique angle measure. So there is an inverse function, f inverse. But f inverse isn't continuous, so f isn't a homeomorphism. Once again, here's the animation that convinces you. Watch it cut. But for good measure, we can also explain it mathematically. Here is an open set whose preimage is not open. Since a continuous function needs every preimage of an open set to be open, f inverse isn't continuous. And therefore f is not a homeomorphism. From the point of view of topology, a good mantra to keep in mind is that homeomorphic spaces are indistinguishable from each other. Any topological information that we have can be expressed in one space, then passed through the homeomorphism to express it in the other space. All that changes from one setting to the other is our perspective. Perhaps the labels that we've assigned to the elements or the subsets change, but not the topological information itself. It's exactly the same idea as the fact that the sets A, B, C, and 1, 2, 3 are the same, just relabeled. That also means that we can find some techniques for determining when two topological spaces are not homeomorphic. We just have to find some topological property that they don't have in common, because then no homeomorphism can exist between the two, since the homeomorphism needs to carry every property back and forth. The homeomorphisms faithfully carry topological information. Let's wrap up today with some properties of continuous functions. Hopefully, when we talked about sequences, non-unique limits, and Hausdorff spaces last week, that discussion put the fear of God into you about trusting your intuition as far as topological spaces are concerned. So I want you to think of the following list less as these are some very obvious facts about continuous functions, and more as, oh thank God, my intuition isn't completely wrong and continuous functions still make a little bit of sense. I recommend that you go ahead and prove these two. They're straightforward and they'll help you to verify that you understand the definition of continuity. No, really, go on. I'm serious this time, prove these. So, first off, compositions of continuous functions are continuous. Also, constant functions are continuous. The inclusion of a subspace is continuous. The restriction of a continuous map to a subset on the domain is continuous. On the other hand, if I start with a continuous function and include its codomain into a larger space, then that's still continuous. But I could also take a continuous function and restrict the codomain to only the image of f, that's still continuous. And if I have a space x built out of a union of use sub alphas, then a function f from x to y is continuous if f restricted to each of the use sub alphas is continuous. And we haven't proved anything today, so let's end on a high note. Here's another obvious fact about continuous functions. Shoot, hang on, this isn't a theorem, it's a lemma. Okay, hang on, hold on, rewind, what do we do here? Oh god, oh fuck. If x is a union of a and b, where a and b are each closed, I have a function f from a to y and a function g from b to y, such that f of x equals g of x for all points in the intersection of a and b, then the third function defined to be f if x is in a and g if x is in b is continuous. Okay, first, just notice that h is well defined, since f and g agree where they're both defined. It's good to get that out of the way. Now, we have all these definitions of continuity on hand, so we can appeal to any one of them. For this lemma, we'll show that preimages of closed sets are closed under H. So let C be any closed set in Y, the codomain of H. Well then, the preimage of C under H is just the preimage of C under F union the preimage of C under G. And since F and G are continuous functions, the preimage of C under F is closed, and the preimage of C under G is closed, since preimages of closed sets are closed. Notice that they're closed in A and B respectively, but since A and B are closed in X, the preimages are also closed in X. Thus, the preimage of C under H is a finite union of closed sets in X. Thus, it's closed itself, and therefore, H is continuous, as we claimed. What are you doing? That's it. That's the show. There's no ending gag. You think I can end an episode? I can barely end scenes. We just go from one sentence to the next. There's nothing here. How do you expect me to be able to...